Okay, let's start. Can everyone hear me all right? Um, am I audible? Can people hear me? Okay, thanks. So, just so you know, like during the lecture, I'll be sharing my iPad screen, so I won't be seeing the chat. Okay, so if you want to say anything to me, including like answering questions, sorry, answering to my questions, please speak to the microphone. I won't be able to see your chat. Okay. And so if there's any like issue with like I don't know, like the lectures, please kind of feel free to speak into the microphone. All right, so I'm gonna be sharing my screen real quick and I won't be seeing your chat anymore. Okay. All right. So like I said, if there's any issue with like the lecture quality, like you can't hear my voice, you can't see uh the notes, whatever, right? Please feel free to let me know. Speaking to the microphone. So, let me go over a few things first before we start the lecture. So this is Math 478, okay? Intro to Stochastic Processes. Okay, so a few things about the class. First thing, of course, is, uh, please read the syllabus because it includes, a lot of details that basically you should know about the class. That's the information that basically is required, okay, by the course coordinator for the summer courses. Now, regarding my class, okay, there are a few things I'd like you to know about the way I run my class. Well, the first thing is that basically I don't do any kind of, regarding exams, okay, this is very important. I don't do any kind of practice exam or review, okay? So basically, if you kind of expect to have a class where the instructor tell you what's going to be on the exam and you just memorize it and go and repeat the same kind of questions on the exam, that's not my class. Basically, for the exam, I will always tell you to study the lecture and the homework. That's it, okay? So nothing about practice exams or reviews. On that note, um, I also won't be able to tell you how many questions will be on the exam, things like that. So if that's kind of your kind of favorite question to ask, that's not something I'll be able to tell you. Now, regarding the grades, again, it will be based only on your performance only. All right. Now, I don't know. Students always tell me that this will be the last semester that they'll be, taking courses. This course will be required for their degree, whatever. Okay. Um, I don't know. I won't take those into account when I assign your grades. Okay. In the end, if your grade is a B, it's a B. It's an F, it's an F. Okay. Um, on that note, don't expect curves or extra credits. Um, I don't do those. I mean, well, if the whole class does very badly, okay, on the exam, there'll be some adjustment. But if like some individuals don't do very well and other people do very well, which tends to be the case in my class anyway, there will be no adjustment, okay? And don't ask me for extra credit, toward the end of the semester. I don't do any of those. So again, right, very straightforward. You have to work very hard in a class like this. Is super challenging, okay, especially in the summer. And you will have to study on your own for the exam. I won't be providing you any help. For the grades, again, right, it's just whatever percentage that comes out. That will be your grade. So if again, if this is not your style of class, I understand. But I just want you to know ahead of time. What else about the course? So in terms of what you need to know coming into the class, so of course the prereq, right, is something like math for 77, intro to probability, something like that. Now, however, okay, like a basic, I don't know, like kind of like a C, let's say, right, in math for 77 tends not to be enough, okay, for a course like this. So basically, even though this is the prerequisite, this course, 478, requires the students to know probability very well. And for some reason, some students, when they take a course like this, maybe not 477, okay? This is just one of the prereqs, I think. At Rutgers, they are not exposed to all kinds of basic probability theory. Notably, basically discrete and continuous random variables. Again, I'm just listing things here that I have seen in the past, but students sometimes told me that they have not even seen any kind of continuous random variable. And that's just not gonna work, okay? So basically, I won't have time to help you review probability. You will jump right into like the middle of like a lot of questions that require you to be very, very well versed in probability. Now, having said that, the kind of the way that the course is going to be laid out is we're going to go over chapters 1 to 4, okay, in the textbook, and chapters 1 to 3 in some way it's about probability, all right, but very advanced. So yes, right, in some way we will be sort of like reviewing probability, but don't take that in any kind of trivial way, okay? Chapter 1 to 3 in our textbook will be very, very challenging. And it will be developing your sense of probability, your knowledge of probability in an advanced way, preparing for chapter 4, which is Markov chain, okay? And in my experience, this is enough for a class like this, all right? So even though the name of the class is stochastic processes, we'll spend a lot of time like developing like advanced probability theory, and then work on Markov chain. So if you look for fancy, I don't know, stochastic processes knowledge, right, like Brownian motion or I don't know, continuous time stochastic processes, that won't be covered in this class. Well, of course, in the end, if we have some time, we're gonna cover some extra materials, but basically, I think it's gonna be on queuing theory, queuing models, okay, if time permits. But my philosophy is that I rather go deep and covers all the ground for the knowledge, rather than go broad that expose you to a lot of things and you end up knowing nothing. Okay, so that's the structure of the course. And again, please take my word seriously that if you're not very well versed in probability, you will have a very hard time in this course. Okay. And having said all that, oh, I guess one more thing. The course is recorded, the lectures are recorded, but recordings are not going to be provided, okay, without reason. So even though the course is online, well, online just means that you can log in and watch the lectures, but it's not asynchronous, okay? It's synchronous. That means that you're supposed to come in, watch the lectures, participate, do all those things just like a regular class. On that note, if you travel, okay, during the class, I guess that's fine, but please make sure that you have good internet connection, especially during the exam. I have had students before who travel and who do not have good internet connection during the exams, who ended up not being able to do the exam, which results in a 0, okay, on the exam. And all those things you should watch out for. This course is not designed to help you to, go on vacation and still, earn a good grade, right, in the class. I guess there's something else I want to say here. What I guess I'll add them when I remember. Oh yeah, I remember now. So there's a component, right, called attendance quizzes or just quizzes. So here's how they work. Basically, again, right, attendance required, and the way I measure them, right, is that I'm gonna be providing you with questions or problems during the lectures, okay? And I'll give you like a minute or so to think about those questions and try to come up with answers. I mean, the point is that you have some time, very little, to try to engage with the materials. I will be providing, right, the answers to those questions after that 1 minute. So basically, the answers are provided to the question. Your task is just to copy down the questions and the answers, and then submit those, right, to the assignment on Canvas at the end of the lectures, okay? Yeah, 15 minutes to do so. Again, right, the point is that to make sure that people don't have time to copy each other, right? Even if they don't attend the lectures. So basically, there's no right or wrong answers, right, to the attendance quizzes. You can basically just take notes, upload your notes onto the quizzes, assignments at the end of the lectures, and you'll get like full credit for those assignments. The only thing I want to say about the attendance quizzes is please don't cheat, okay? Again, this is just my way of making sure that students come to class and get rewarded for coming to class. But people have been abusing, right? This kind of system from as far as I remember. They don't come to class, but they will submit something, or they would borrow their friends' notes and they will upload the same thing. All right. So let me tell you that normally I won't check the attendance quizzes. If you submit something, you get full credit, right? Because basically there's nothing to check. But if I catch you cheating on the attendance quizzes, you will get 0% on the quiz category. All right. So basically that's 10% off the whole, grade for the course. And only one time is enough, okay, to result in 0%. Like basically all your scores will be wiped out for the semester, right? Doesn't matter in the past and the future. So the reason is I don't have time, okay, to catch cheating in this kind of manner. So please, right, if you don't come to the lecture, that's fine, right? That's just like one time and won't hurt your grade anyway. But if you cheat and if I catch you, right, I mean, basically your attendance will be recorded on Zoom anyway. So I have plenty of ways to check, that. So just make our lives easy and try not to do this. So I think that's all I want to tell you about the course. Is there any question for me before we begin the lecture?
Yeah, I have a quick question.
Mhm.
When we submit the attendance quizzes, do you want like our full notes, or do you want just like
Well, so
separated?
technically speaking, right, you only have to submit the questions and the answers, but that takes work. So if you do the full notes, I accept that as well, as long as it contains the questions and the answers, right, that were gone over within the lecture. Is that okay? So either way is fine.
Yeah, that works.
But
Thank you.
I think that the notes is easier for the students to upload because they take the full notes. But if you don't want to and you just want the question and answer, that's fine. All right. Any other questions? All right. Very good. So during the lecture, if there's anything that's unclear, any questions you have, feel free to speak in the microphone and interrupt me. Okay, I'm perfectly okay with that. Basically, like I said, I won't be able to see a chat, so the only way you can interact with me is through the microphone. So just stop me, right? Just like a regular class. I won't be able to see you, but I can hear you. Okay. All right. So today's lecture, we're gonna go over, chapter 1. I don't know how much we'll be able to cover, but basically, the title of chapter 1 is, in Ross, is Intro to Probability Theory. But basically, you can think of this as a review. Okay. So the sections we're going to go over for now, let me see, is, let's say 1.1 to 1.5, which cover the following concepts: sample space, events, let's say law of inclusions and exclusion, conditional probabilities, and independent event. Okay, so we're gonna just kind of talk about these things real quick, and I'm gonna give a bunch of problems, okay, to demonstrate, or maybe 1 or 2 problems to demonstrate these concepts. So the first thing, right, is that basically when you talk about probability, there's always a sample space implicitly defined, okay? So basically a sample space has the following. It has omega, which is your universe, right? Basically it's the collection of all events. And then of course, right, the events have certain kind of rules, such as countable unions of events is event. Okay, and countable intersection of events still. All right. And of course, the complement, right? If E is an event, then E complement is an event. All right. So the word countable, right, is a word that you will see in a class like real analysis. All it means is this, right? If you have E1, E2, etc., right, up to whatever, right? The infinity, there's no such thing, right? But if you just count up events, etc., right? There are events, then the union of these guys are events, and the intersection of these guys are events. well, why do we care, right? Why do we keep repeating the word event? Basically, events are things that make sense for you to talk about, like for you to apply a probability onto. So basically, you can write this probability of this, probability of this, right? All of these make sense, and probability of E complement, for example. All of these make sense. So basically, think of it like an operator, right? And the domain of such operator. So these rules guarantee that it's legal for you to talk about probability of union of events, intersection events, and complement events. Okay. A lot of times we're going to do finite union intersection, and that's hard enough. But just in case, right? Sometimes we do go to infinity, but in a countable way. So that's there to ensure that. So again, right, this is like a formal setup of like a probability, theory with sample space. But so a lot of times, right, the universe and the collection events are implicitly understood. You don't have to really list out, all these things. Like you don't have to list out omega. So a lot of times it's implicitly understood. Right. For example, I'm just gonna give you a very mundane example. Like you toss, let's say, a coin twice, okay, or two coins, whatever, and you look at the result, right? Then obviously the sample space will be something like head head, head tail, tail head, tail tail, right? Basically, these are all events, are all possible. Well, okay. So I guess there's something here called all outcomes, right? Outcomes are like elementary events that there's nothing smaller than that, right? So these are all possible outcomes. Let me just say that. So event is like a atomic, right? Outcome, right? It's just sorry, outcome is like an atomic event, meaning that there's no small event than that. But of course, right, you can talk about an event like this, right? Head head, head tail, right? Something like that. So basically, so when we do comma like this, right, that means or, right? So event E, when I describe like this in English, right, basically means what? First toss is head, right? Okay. Now, of course, you can do more events than that, right? You can do first toss is head, second toss is tail, which is head tail, which is an outcome, for example. But basically, when you combine, right, when you combine events using the union operator, right, it's still an event. So you could top a probability of this, for example, right? So, well, so all this is mundane, but we want to mention this. The reason is sometimes, okay, depending on the problem, you'll see that switching sample space somehow helps you to change your point of view and see the problem in a different way. So one thing about Ross, okay, about this textbook is that the problem won't be given in a symbolic way. A lot of problems, so the title of this textbook, right, is Introduction to Probability Models. So the problem in Ross are word problems. All right. And basically, one of the challenge in this textbook is to translate them into a probabilistic framework. All right. And the first thing you should do or you must do when you translate a word problem into a probabilistic framework is to choose your sample space, choose your universe. Okay. And we'll do a problem real quick. Real soon about the choice of how the choice of the universe or how the choice of sample space will change the way you do the problem. And that actually is one of the challenge in a class like this, that basically there's no formula, okay, to solving a problem. In contrast to say math 477. I'm not saying that 477 is easy, but I think there's certain problems when you apply a formula, you get an answer. In this class, right, you will most likely encounter this step to begin with. So the choice of the framework is going to be very important. So let me just say, right, the choice of omega, choice of sample space, basically implies a choice of a perspective into a problem, okay? And choosing the right perspective to the problem will decide whether the problem is easy or hard. So again, this might sound abstract right now, but I'm going to do a problem to demonstrate this to show you. But that's why, right, sample space is important. In the abstract, it means nothing, but in concrete, it basically means how you choose to model, okay, the problem, and that will change everything. Now, let me see if we have enough to continue. Okay, so let me say real quick about this. So conditional probability, which is one of the topic, right? So this is actually very, very deep. But right now, I'm going to mention a basic definition, and then we'll do a problem. So when you have two events, right, E and F, then the probability of E condition on F, right, by definition, is P of EF over P of F. Of course, right, provided that P of F is non-zero. So here, the notation EF is a shorthand for E intersect F, all right? So in this class, when we have two events, or in ROS rather even, right? When you write the two events together without any notation, that means intersection, okay? I mean, if you want to write down the whole intersection, that's fine. But, you know, just so you know, right? When we write like this, that means intersection. So, well, first of all, right, this is just a definition. But in terms of the concept, right, what does this mean? Well, first of all, right, in terms of the Venn diagram, if you have E and you have F, right? So this is EF, right? E intersect F. So you see that PEF, right, represents basically how, you know, how wide, right, how big this part is. And divided by PF means that you're looking at the relative weight, right, of this portion with this portion. So in that regard, right, what you're thinking of when you do this formula is that you assume, well, you basically are saying, right, that F has happened, right? That's your knowledge. You know that. So basically, yeah, here's the thing, right? Conditional probability effectively changes your universe. Okay. So you have some universe before. Okay. So I guess I haven't drawn that here, but there's kind of like a big universe that you operate within, right, called omega, in which, right, E and F are events. But when you do P of E condition on F, effectively you change your universe, or you change your point of view from omega to F, okay? So you have more knowledge. Conditioning means you have more knowledge. You know F has happened. Previously, right, you know nothing. So basically, when you have your generic sample space and you don't say anything, basically omega means no prior knowledge. So you do all your probability with no prior knowledge. But when you do P of E given F, so when you do PE, right, it's like you do P of E condition on omega, if you will. But this is an empty notation. That just means that condition on the whole universe, meaning that you know nothing. So basically just PE. But when you do PE given F, that means that you know F has happened, and you weigh, right? You weigh the likelihood of E, right, relative to F. Okay, so that's conditional probability. Now, so already, right, you see in this concept, sort of like the perspective changed. Now, so with this definition, right, comes the definition of independence, right? So E is independent. E and F are independent because this is symmetric, right? So the notation I will write in this class is the following, right? I mean, this sort of like it's orthogonal too, right? It's a geometric notation, but in this class, it just means that two events are independent or a bunch of events are independent. If, right, this is the definition, P of E condition on F is P of E, okay? So again, I think you guys have seen this before. This is nothing new. Basically, the two events are independent if, right, condition on the knowledge that F has happened does not change the likelihood that E has happened, right? Or doesn't that E will happen, right? So in this sense, whether or not you know F has happened doesn't change the likelihood that E will happen or not. Of course, right? I mean, this is enough for the definition, but you can also see that this is equivalent to saying, right, that P of F condition on E is P of F, right? So again, right, it makes sense because if they're independent, then condition on one event has happened doesn't influence the likelihood of the other event. Of course, right, the student's favorite definition is P of the intersection is the product, right, of the individual probabilities. Okay. Now, I say this is the student's favorite definition because somehow it's kind of easy, right, to calculate the probability intersection using the product. On the other hand, right, please note that I think this one is the hardest to interpret. When you move to a class like this, it's not enough just to memorize formula. It means nothing. You have to interpret the formula to see what it's trying to tell you. In my opinion, right, these formulas mean a lot because it kind of tells me why we call two events independent. Again, this means something, but the intuition is not as deep. Of course, the math, right, say that they're all the same, but right, you want to carry your intuition into this kind of formula, which is going to be, I would say, sort of required, right, to be able to do well in a class like this. All right. So let me see here. Now, having mentioned all these things, right? Well, conditioning and independence will be, revisited again in a very, very deep way. But right now, let me just do a problem in which I would call it a quiz, right? Quiz one. So quiz one just means that it's the first question of the day, instead of calling question one, quiz one, right? So this is those kind of questions that you have to write down the question, the answer, and submit it, right? At the end of the lecture. So the question will be the following. It's going to be question number 12 in chapter 1. At the end of the chapter 1 in the textbook is as followed: that E and F be mutually exclusive. Okay. So basically, of course, what that means, right, is E intersect F is empty, right? E and F has nothing in common. That's what it means to be mutually exclusive. Suppose, so let me say this. Let me just write the whole language here. In a sample space, in the sample space of an experiment, Okay. The experiment is repeated until E or F occurs. Find the probability that E occurs before F. Okay, so that's the question. So again, I'm going to give you like 1 minute to try your hand at this question, and I want to ask if anyone has any answer. Right, the point is not for you to find, the perfect answer here. The point is for you to interact, with me, with the materials if you want to. So there's no, kind of shame, right, in saying the wrong answer or anything like that. But please try to kind of think of the question so that you will be able to understand the material better. I mean, if there's anything that's unclear about the question, you can also ask. Okay. Does anyone have any suggestion for how to approach this question or the answer if you have? Okay, I'll take that as a no. So first of all, right, notice that the point of this kind of questions is exactly, even though they're a probability question, they're not the kind of question I think you would see right in a typical probability class, right? It's especially language like something before something. All right. Now let me say this is the occasion for me to kind of clarify for you what it means to be a stochastic process, right? Which is the name of the class, right? Introduction to Stochastic Process. So the word stochastic process basically means, right? Stochastic means random, right? So something to do with probability, but the word process basically means time. Okay. So you notice, right, that when we talk about probability theory, there's no time dimension involved, right? Basically, I mean, there could be, but it's implicit. But when you do stochastic process, then the time dimension, right, becomes explicit, or basically it's there in the problem. So I'm saying this because, as I mentioned, right, we're going to be focusing on chapters 1 through 4, right, in this class, and only in a way, chapter 4 is Markov chain, chapter 1 to 3 is something else, it's probability. However, right, the component of stochastic process is already there in chapter 1 to 3. It's just not explicit. For example, right here, the probability that E occurs before F, the word before, right, is of course like a word that refers to the time aspect of things. So this is like to tell you that chapter 1 to 3 is not going to be trivial, it's not going to be irrelevant. It's just not explicitly process, but it's there. Okay. So, okay. Now, I would say that normally, right, when a student think about this question, what's in their mind, right, is the following. Well, so first of all, right, there was the word sample space here, right? That's kind of like thrown in for whatever reason. But so there's some sort of like sample, there's an experiment, let's just say, right? And then you just repeat the experiment until E or F occurs, right? That's the key word. Until E or F occurs. So, I mean, I guess basically, if you don't put too much thought into this, what you'll be doing is you're going to think, right, okay, I'm going to count it one by one. So you basically, right, have an explicit time dimension here, right? Basically, the first experiment, the second experiment, the third experiment, so on and so forth, right? On the first experiment, you can have E happening. So obviously, right, it's E before F. Or you can have two experiments in which F happens on the first experiment and then E happens on the second experiment, right? I mean, I'm doing the 1 and 2 here to kind of show you the time dimension, right? First experiment, or first trial. This is the second trial, right? So you know what I'm trying to say, right? So basically, this is F happens and then E happens, right? So that's E before F. Sorry. Not like that, right? E before F. So basically, neither E or F has happened, right? On the first trial, and E happens on the second trial. So E or F, right? Complement like that, right? On the first trial, and E happens on the second trial, right? And then repeat, right? E, no, not E or F happens on the first trial. Neither E nor F happens on the second trial. And then E happens on the third trial, right? So on and so forth. And you have to, so these are or, right? Either E happens on the first trial, or either F happens on the second trial, and then E happens on the first trial, E happens on the second trial, and so on and so forth. So basically, when you do this, you have an infinite series, and then you add up, right, all the probability of these events, and then you will get the probability of E occurs before F. All right. So basically, this is an okay way to do this problem, but it's going to be complicated. That's all, right? I guess I'm going to show you, right, the answer to this question, approaching this way to convince you that, when you approach the problems in different ways, you'll get to the right answer anyway. But what is the easy way to do this problem, or the right way, or the simple way? So let me say the simple, okay, perspective is the following. And which is like a lot of times, right, simple is equivalent to right in this class. Because like I said, if you do a complicated model, the first thing is it's very hard to keep track of things, right? Like for example, I wrote down the wrong, right, event, right, for the first trial, right? It's supposed to be E union F complement rather than F, right? Things like that. So the more complex the way you think about things, the more likely you're going to make an error, right? Period. And the second of all, right, if it's complicated, maybe your math won't work out. You just can't keep track of things. So that's why simple usually is equal to right in this class. And that's, again, let me repeat, that's the hardest challenge, right, for this particular course. That students always show me certain ways that they do the problem, and I myself won't be able to tell you that it's the right way or not, because I don't even understand what you're trying to do. Right? Basically, your perspective is not right. And so coming up with the right perspective, right, whatever that means, is going to be the thing here. So what is the right perspective? The right perspective has to do with changing the way you see things, or changing, so to speak, the sample space. How so? The reason is this, right? You basically, the experiment is repeated until E or F occurs. So basically, you're effectively saying that your sample space now, the universe, is changed to the union of E and F, because you know either E or F has occurred. So, or basically, this is the language that kind of signal to you that is conditional. You know that in whatever that you're interested in, E or F will occur. So that's conditioning. But within, right? So within that new universe where you know E or F has occurred, what do you want? You want E to occur, right? Because you want the E occur before F. So first of all, you change your sample state to change its perspective to conditioning, right? On, let me just say conditioning on E or F has occurred. And then the probability that you want, the answer is just P of E condition on E union F. That's it, right? Once you know that E or F has occurred, then you want that E to occur before F, which, right, according to our formula, is the following, right? E intersect with, here I would write intersection out explicitly because, you know, I just want to kind of like this. And then, right, if you want to use the fact that the events are mutually exclusive, the answer simplifies down to like that, okay? Which is the answer that the textbook would like you to show. So when I write down the answer, the question here, I hide this part. The way the question asks is like, show that the probability that E occurs before F is this quantity. But I think that, right, again, this quantity is very misleading because it doesn't tell you the whole story. The whole story is right here, right? E condition E union F. This is just a workout of this formula when E and F are mutually exclusive. Does that make sense? So that's the answer. Now, the next thing is going to do some twist to this problem, right? When E and F are not mutually exclusive. And then I'm going to show you how this approach gives you the same answer, right, as this, to kind of give you the full depth, right, to a problem. But let me pause here and see if there's any question.
So I have a question. This would be like a geometric distribution, right? So you're summing all the possible geometric.
Okay, so it's okay that you think about the geometric distribution. It has that flavor. But I would say that the analogy stops there. And
Yeah.
that's the danger of a course like this. Basically, yes, but no, in the sense that the geometric distribution is about waiting for an event to happen, right? Waiting for the first time that an event happens. But technically speaking, you're not doing until E or F occurs. You do within that, then you want to know E has occurred before F. So, you know, it's more subtle than that, right? So yes, the answer is yes and no. So yeah, I mean, if you know what I'm trying to say, then sure. Okay. Yeah, I mean, of course, this is a geometric series right there. But yeah, it's slightly different. Any other question? Okay. So you know what? So let me move on to the second question, right? Quiz 2. And here, I guess since there's a question like that, so let's call this approach 1, right? The complicated approach. This is approach 2, the simple approach. Show that the approach 1 gives the same answer as approach 2. Okay. So again, this is just for educational purposes. Okay. Basically, this is like an advanced way of thinking, I would say. All right. Don't take any simple approach to be simple to understand. Usually, simple approach are hard to understand. That's why people don't find them immediately. Okay. So even though we call them simple, please take a lot of time to make sure you properly digest why they work this way, blah, blah, blah. Okay. Now, the complicated approach usually are the easy one to understand in a way that, in the sense that basically it's the natural thing you stumble upon. And you know, when we have a lot of time, this kind of question can be educational, right? To make sure the different approaches give the same answer. But let me caution you that a lot of times we don't have time to do this kind of thing, right? The whole point of this course is to give you an education on the new perspective so we don't repeat the old perspective a lot of times, okay? I'm saying this because like some students will come to me and show me their approach and ask me to verify that it works in the same way as, you know, let's say the class's approach, which, you know, in some way is valid when you study math, right? Because you probably will hear your teachers telling you that there's no single right answer to math, which is kind of correct, but also not correct in this way, that basically, you know, you can either walk or take a car. No one will entertain walking when you can drive. So same thing here, right? I may not be able to work out, right, the complicated approach with you on every single question. I will rather ask you to verify it on your own, and I will only teach you the, you know, let's say the simple approach. Okay. So just a warning ahead that, you know, you seriously need to adopt a new perspective when you study this class. We're going to do this just to convince you the value of the new approach. We're not going to, you know, keep doing this all the time. Okay. So let's see how we do this. Now, sometimes, right, even so when you do a complex calculation, some sort of control notation will help, right? Just to make things easy. Well, of course, right, a student already mentioned, right, that we foresee a geometric series coming up, right, an infinite series. So it probably won't really be very fun to write down a lot of notations. So maybe the first thing we should do is like somehow reduce the notation to something like this, right? Give it some letters, P and Q, in which case P of E union F complement, right? Neither event has occurred will be 1 minus P minus Q, right? Okay. So you see, right? The reason is basically then, right? What is the series? The series will be, right, either P or, right, 1 minus P minus Q times P, or 1 minus P minus Q times P squared. Sorry. Square, right? and then 1 minus p minus q cubed times p, etc. Right? Which again, already note what E has happened on the first trial. Neither E or F has happened on the first trial. E has been on the second trial. Neither E or F has happened on the first two trials. E has been on the third trial, so on and so forth, right? Okay. All right, so what does this sum up to? Oh, by the way, right, we will see geometric series in this course, so you should know your geometric series. So it's a geometric series with what kind of ratio? The ratio is this guy right here, right? This is R. So the formula for a geometric series is that it's the first term, which is P, divided by 1 minus the ratio, right? Of course, this series converges because the ratio is less than 1, right? I mean, between 0 and 1, right? So this is 1 minus P minus Q, which, as you can see, will be P over P plus Q, which is this answer right here. Is that okay? Any question? So again, right, I mean, I would anticipate that some student would actually claim that, okay, then actually this is the easy approach, because as long as you can master the geometric series, then you can write down all these things and you can, you know, come up with the same answer, right? Or you don't have to twist your brain into changing perspective, blah, blah, blah. Okay, fine, right? You could see it that way, but trust me, right? This overall will be a more holistic approach, a deeper approach, because we will not just keep doing this in this class. So as a demonstration, let me do another quiz. So basically, let's say repeat the same problem, right? Repeat question 1. But without the assumption that EF is mutually exclusive. Okay. So basically, here's the thing. Again, in a class like this, right, you have a problem and you can twist it in many ways. You can approach it using, you know, different perspectives, or you can change the assumption and, you know, it may or may not become a different problem. But assumptions, right, will be a very important part in class, and you'll see. So basically, just when we do a problem, it can be deep, and we can, you know, just change a few minor things. It may or may not become a hard problem. So, right, let's just see if we can do this, or, you know. All right, any answer to this question?
I have an idea, but I'm not sure if it's correct. So because now
Yep.
because now you can have intersections,
Mhm.
I changed the formula. I changed P to No, I changed P1 minus P minus Q to 1 minus P minus Q plus PQ because the intersection, now you add the things, the intersection is
Okay.
taken out
Yep.
twice.
So, all right. It's both a good and a bad idea. I mean, I know obviously what you're trying to do, right? So, in case you guys cannot catch what your friend is trying to say, he's actually obviously thinking of the second approach actually, and he's changing, right, this quantity to 1 minus P minus, let's say this, P is actually this, right? P plus Q minus PQ, right? That's what you're saying. And
Yeah.
we know what that's called or what that's based on. Actually, right, that's a bridge to the next topic we're going to be talking about is called the inclusion exclusion formula, right? Which says what? That probability of the union, let's say of only two events, we're going to talk about n events, is the sum minus the intersection, right? Which obviously comes from the Venn diagram, right? Where if you have E and F, and if you look at the whole thing, right, you take E, you add F, but then you see that you add this twice, so you subtract the intersection to, properly, right, not double counting. All right, so several things here. The first thing is, right, it's very understandable, but you, by default, go with the second approach, which, as I kind of warned you, right, is the old way, whatever, I understand. But also at a demonstration, you kind of make a serious mistake here using that approach, which is what? It's not about the approach, it's a serious mistake that students always make when they do probability. The mistake is to
I'm not sure,
assume.
but
Yeah,
yeah.
go ahead.
Yeah, so PQ doesn't necessarily PQ happening, like both of them happening at the same time doesn't necessarily mean one happened before.
No, that's not that. Again, so now you're mixing up concept, right? First of all, again, this problem, even though simple, is deceptively simple. It's complex. Try to think about it. First of all, there's no such thing. Okay, yeah, PQ can happen at the same time, which means here that the intersection of P and Q, right, or E and F. But that's not your mistake. Your mistake is to equate P times Q with PEF. Because what are you saying? You're saying that PEF is PE times PF. Agree? Now, what does that mean? That means that E and F are independent. Is that anywhere in the problem?
No,
Correct.
no.
So that is actually a favorite mistake of probability students. They always assume events are independent when they are not, or when there's no such assumption. So exactly the point of inclusion exclusion formula is to handle that, okay? So it's okay, it's a very understandable mistake, but this is a no-no. You cannot assume that unless it's explicitly stated or you prove it somewhere, right? So, okay, it's a good approach or it's a good try, but again, right, revealing these kind of like common patterns that students tend to make. The answer to the question actually is easier than you think. The reason is this, right? If you look at this solution, right, up until this point, does it rely on the fact that E, A, and F are mutually exclusive? Meaning the answer up to here, right? Does it depend on the fact that E and F are mutually exclusive?
No.
The answer is no. Correct, right? It's just a conceptual argument. So therefore, actually, the answer is still this. Now, which means it's still this, because this is just definition. The only change is down here where obviously this is no longer correct because E union F, right, is no longer just this. So the answer actually, right, is just going to be P of E conditional E union F, which works out to be P of E divided by P of E union F, which works out to be, if you care to write down, that's it. That's the answer. But we don't know anything about this quantity and we don't care. So what I'm trying to say, right, is that exactly, you see the danger of following, let me say, the old approach or the complicated approach is that you can swap in certain things and not paying attention to the overall structure of how the problem would interact. Maybe that way, I don't know. But if you just follow the argument or you understand the concept of the new approach, you'll see that, you know, again, the assumption doesn't change anything about the essential structure of the argument. And again, I like to say that that's the value, right, of the new approach, or of the, you know, the approach of this class. Okay, so this is the answer. Period. I mean, of course, if you do this approach properly, you will get to the same answer anyway. But you know, any question? All right. So maybe actually on that note, let me give you another question. It's not quite related, but here's a question. Suppose E and F are mutually exclusive. Is it true that E and F are independent? Because I don't know, I'm not sure. There's something along that line that caused the thinking that, right, the events are independent in the previous answer, but right, mutually exclusive events, are they independent? All right, any answer here? All right, so first of all, right, when you see a question like this and you don't have a clue, probably the best place is to go back to the definition, right? And the definition of independence means what? You know, you can do whatever you want. You can do this, right? Or you can do this. Right? But either way, right, what do we see? Because E and F are mutually exclusive, P of EF is
0.
Correct, right? Because an empty event is 0. Now, on the other hand, right, this is guaranteed because EF are empty. Is it true that then 0 is equal to P times PF? The answer is no, right? Unless both of the events are, somehow have 0 probability, right? So the answer here is no, unless both PE equals to PF equal to 0. Okay. So in other words, right, the answer actually is the opposite. If EF are mutually exclusive, that usually actually that must mean that E and F are not independent. All right. So again, concepts are related in these ways that you may or may not have thought about, but it's something that you kind of like want to be able to do very fluently, okay, in this class. Now, is there another intuitive way for us to think about this? Well, of course, right, this is the way. This is like the rigorous way, okay, to show the answer because you rely on the definition. But if you want to apply an intuition, well, what do you want to say here? Well, if E and F are mutually exclusive, what that means is that if we know that F has happened, then we also know that E cannot happen, right? Because they're mutually exclusive. And again, right, what is the spirit or what's the intuition of independence? Independence means that whether or not F has happened does not change the likelihood of E happening. Meaning, right, that the knowledge of, like, basically whether F has happened or not does not affect E. So this right here exactly is the opposite, right? If F happens, then E cannot happen. So therefore, there's no way that they can be independent. Okay, so that's the intuition. Any question? All right. So now let us continue to the next topic, which is, what I was saying, right? Inclusion exclusion formula. So at the very basic level, right, it says that the union of two events, right, is the sum subtracting the intersection, right? Now, of course, the point is to generalize this to more than two events, right? And I hope you know the answer. Basically, it's the sum at the first level, right? And then subtracting all the intersections. And then add back up the third level, right? Like that. Again, of course, this form is tiresome. I mean, not tiresome, but want to write down as a sum, right? In a series formula. But just in case, right? Can we prove this? Do we know why this is true? Well, besides writing down a Venn diagram of like 3 events and count it up in a very complex way. What's the proof of this? Or why is this true? How do you know that besides the fact that I just write it down? So the answer is, you can always look at this as two events, right? Like that. And then of course, right, you can use the first law, right? And then, right, you continue to develop, right, using kind of the first law, right, with two events. Is that okay? So that's the way you can prove this using the first law. But what do I want to say here, right? So let's write down the general, right, formula. So the general formula is, let's just say finite, okay? So it's a finite intersection. I don't care for infinite intersection. Just, oh, sorry, finite union, right? So 1 to n. Well, so whatever n is, right? It can be 2, 3, 4, 5, etc. So what's the formula? The formula is just like going down by layer, right? So the first layer is you sum up all the unusual probability. Then you subtract all pairwise intersection, right? But notice that you only do it once, right? So if you do something like this, you will basically do it twice because, you know, I 1, 2, and 2, 1. So you want to do I less than j, something like that, right? To make sure you only do it once. And then of course, right, you do it, you know, at the third level, right? Something like that. But so basically, eventually, what's the formula? The formula is that you do -1, right? Raised to what kind of power? Raised to a power of n plus 1, or, you know, basically, right? If you have pairwise and you subtract, you get 3 of them and you add. So that's why, right, the power is always -1 raised to how many, right, intersection you have plus 1. But the last layer, right, is going to be all intersection, right, like that. So this is called the inclusion-exclusion formula. Any question on this? Okay. So the first thing, right, is what's the use of such a formula? Well, I mean, obviously, right, the use is to compute probability of a union. All right. I mean, again, unless events are mutually exclusive, right, this formula is generally wrong. Okay. So mutually exclusive means, right, all events have no intersection, and that's why all these terms are 0. But in general, right, you have to carry out all the intersections, right, until the last layer, unless for some reason you know that, you know, some layers start to be 0, right, because they are empty. So that's obvious, okay? And we're going to do a problem to demonstrate this. But the other use, surprisingly or not, is to compute the probability of the intersection. Let's just say, so basically when you calculate you want to compute probability intersection, right, of EF or EFG, whatever. Again, right, the temptation for a probability student is to write this down. Okay, again, with no, critique to the student who just gave the answer before. In fact, it's very good that you mentioned this, right? So we have a chance to kind of show the tendency, right, that students make mistake in. But basically, right, like I said, that's a no-no, okay? It's more common than you think, especially when, there's nothing better to do. The students always like to do this because that's the easiest way out. But trust me on this, right? If you take the easiest way out and there's no understanding in your answer, then you get no partial credit to the question on the exam, and which will result in a 0. So take your time, right, to appreciate the problem and try to use the right approach. Taking the shortcut in a problem in a course like this will most likely result in a wrong answer. So, right, well, what does it mean to compute PEF? Well, the answer is right there, right? Well, because PE union F is like this, therefore, P of the intersection is just this. No more, no less. Again, right, it's kind of, I don't know how to say this, it's sort of disappointing in a way, because in your mind, right, you shouldn't be able to tell this immediately. Well, the answer is not really. If there's nothing given about such an event, there's nothing simple about this question. In other words, right, something gotta give. In other words, if you want to know the probability in intersection and you don't know the independent, then you should also know the probability of the union, and vice versa. Okay. So again, a more mature person always make sure they have all the pieces of the puzzle right in before they can tell you that they know the answer. So we try to see if there's a question that demonstrates this concept. Okay, so let's maybe take question 8 in the chapter. So this is quiz 5, right? This is chapter 1, problem 8. So it says this: if P of E is 0.9, P of F is 0.8, show that P of the intersection is no less than 0.7. All right. Anyone has the answer here? All right. So first of all, right, notice that. So what's the flavor of this question? What's the message? The message is kind of something like this. If two events are big, I mean, if two events are likely to happen, then the probability that they're happening together is also big, right? That's it, right? If two events are big, then the intersection is big, something like that. Now notice, right, that if we go with, again, the student's favorite kind of formula, then we get that P of EF is PE times PF, which is well, actually, in a weird way, right? It shows this, which is true. Sorry, which agrees with the conclusion, but in fact, right, is the wrong answer. Okay, so yeah, I was expecting that this number is lower than 0.7, but no, it's actually higher than 0.7. But okay, it's just a coincidence, right? Again, this is the wrong answer. So what's the right answer? The right answer again is through this formula. And again, right, notice that the question gives an inequality. It does not give an exact answer because we don't know, right, the union. But so the probability of the union. So what is it here, right? PEF, right, which is what we're trying to calculate, is PE plus PF minus P of E union F. Now, what do we know? We know this is 0.9, this is 0.8. Do we know this? Well, the answer is we don't, right? But we're not asked to calculate exactly what this is, right? We're only asked to give an estimate. And what do we know? We know that P of E union F must be at least, sorry, at most 1, right? I mean, that's just how probability works. Therefore, subtracting this means that it's greater equal to 0.9 plus 0.8 minus 1, which happens to be exactly 0.7. That's it. That's the answer. Any question? All right. So now let's move on to one of my favorite question for this course. The reason is, right, this question, which is going to be like a model rather, will be sort of reappearing throughout the course, demonstrating a different concept, right? So we'll give it a name. It's called the hat problem, which probably is a name that some other book will also use. So you probably have heard of this before, right? The story is rather mundane. Basically, there's so many gentlemen who throw the hats together, right? Let's say 3 men, right? Throw the hats right together and then pick them out randomly, right? Okay. And we want to know the probability that, okay, so let's make it easy for now. All men get the right hat. Let's say this is A. Okay. What's the answer here? This is an easy question.
1/6. I got 1/6.
That's correct, right? That's exactly it, right? The answer is 1/3 factorial, right? Because there's only one outcome out of 6, right? In which all men get their right hats. Is that okay? Okay, so maybe let's try B. Exactly one man get their right hats. You know what? Hold on. Let me try to think here. No. Let's go to the meat of the problem. So this is just a warm-up, really, right? This is not really what we're after. The question is, no man gets the right hat. Okay, so I think this is a small enough problem, so some folks can maybe list out all events and count it up. Did anyone do that? Anyone got the answer that way? So in other words, right, if you do 1, 2, 3, you can count all the ways you can assign, right? You can commute the entries so that things don't match, right? That's one way. Another way maybe is 2, 3, 1, things like that, right? So, but the point, right, is that this is not going to work if we scale the problem to 10, 20, or n men, right? So in other words, I mean, this is a problem well known in combinatorics as well. I forgot what the name of the concept is in combinatorics. But basically, it's a way to permute, right? The numbers so that none of the numbers is in the right order, right? But so in terms of probability, what are we thinking of? So I guess, yeah, long story short, I hope you appreciate that unlike this question, this is rather a complex question that needs to be approached carefully. Okay. And when we say we approach something carefully, it starts out with some kind of modeling. So what are we modeling, or what are our events, for example? So the events that we're interested in would be something like this, right? And again, this is like, you know, the way you approach a problem, you write out a framework. So you let E1, right, E2, E3 be the events that, right, the men number 1, number 2, number 3, etc., right? Guess the right hat. Okay, I hope that's clear. So that's the event, right? So now what are we after? We're after the event that no man gets their right hat. So we're after this. Agree? And notice, right, with our notation, this means intersection, and, right? So this is an and event. All right, so maybe let's just try some concept here. And this has nothing to do with the question, but are the events mutually exclusive? Let's just say that that's just a language, right? See if you can parse the language. Are the events mutually exclusive? And what do I mean when I ask that?
It's not mutually exclusive, I'd say.
Yeah, that's correct, right? So first of all, right, what I mean is that they have nothing to each other, right? Now, of course, that means that the intersection at any level must be empty, right? Or let's say at the pairwise level, right? They must be mutually exclusive. So basically, this is a question, right? Just to test this out, would E1, E2 have empty intersection? And in English, right, what does this mean? This means that is it possible or is it impossible, whatever, however you want to put it, that the first and the second men get their hat right, get the hat correctly? And the answer, of course, is possible, right? Because, you can have, of course, I mean, if the first and the second gentleman get the hats right, then also by, default, right, the third man also gets the hat right. But the point is that, right, it's not mutually exclusive, right? The answer is no. Okay. Again, I mean, this has nothing to do with the question in hand, but I just want to demonstrate, right? These are things you just throw out to make sure you interact with the question so you understand what you're dealing with, right? When you're solving a problem. Now, back to the real question, right? This is what we're after. And again, you kind of see that, right? Maybe one of the message I say above here, right, is that basically intersection to calculate the probability intersection, you most often cannot do it directly. Or maybe, right, let's just carry a thought out. I never think about it like this, but let's say R EI complement independent. Because, right, if somehow by luck they are, then the answer is something like this, right? In which case we're done. But is it true? Are these events independent? Well, so first of all, right, you could have an intuitive answer. The intuitive answer is probably not, as I hope you would come up with the same answer. Why so? The reason is, right, it's kind of clear intuitively, at least, that the action of one man here affects, right, the action of the other man. How so? Right? For example, if the first man gets gets the wrong hat, meaning get a third man's hat, then by default, right, I mean, sorry, by logic, whatever. The third man also cannot get the right hat, right? Because the first man only get his hat, so third man also cannot get the right hat. So in other words, right, if the first man gets the wrong hat, then in a way, the other two guys, one of them must get the wrong hat, right? In other words, probably not. Or you can prove if you have time, no. But the point is this, right? I haven't shown you, okay, rigorously that then no, but I guess I have shown you how 90% chance that then no. In other words, when you encounter a problem like this, I guess it's safe to assume that they're not independent. Or you just run some sort of intuitive argument in your mind, right? And then you go with the orthodox or the rigorous approach. So again, right, going back to this theme that to compute the intersection, you have nothing better than the inclusion exclusion formula. Okay. So basically the hat problem is a classic demonstration of many formula, one of them being the inclusion exclusion formula. So, but before we do that, because of the complement here and because of De Morgan's law, right, there's something better we can do here, which is that we can turn this into right the complement of the union, right? The complement of the union is the intersection of the complements, right? Like that, right? So anyway, the point is, you can work with inclusion exclusion formula, I think, at this level, but it's kind of like nasty, I think. So you turn it like this. There's another deeper reason why you want to work at this level. But the point is, right, this question, even though this is what we're after, the indirect formula is to somehow look at this. And if we can answer this, then we can answer that. Okay, so far? And now how do we answer this? Well, obviously now, right, this is in the context of inclusion exclusion formula, which is P of E1 plus P of E2 plus P of E3 minus P of E1, E2, E1, E2, E1, E3, E2, E3 plus like that. Okay. So now let's fill in the blank. What's P of E1? What's P of E1?
Is it just 1/3?
Correct, right? E1 is probably the first man getting his right hat. From the first man's point of view, right, there are 3 hats total. They're all equally likely. So the first man will get his right hat with probably 1/3. And since everything is symmetric, it's the same thing for the other 2 gentlemen. What about E1, E2? What is that probability?
Zero,
Why?
because if the first and the second gets the right hat, then the last one has to get the right hat too.
So why does that mean it's 0?
It doesn't mean it's 0.
No, all you're saying is in this particular case, these two events are the same, which is true. That doesn't mean that's 0, right? Well, exactly, right? That's the question here. Are they mutually exclusive? We say no already. And what did we say about this intersection? It's 1/6, right? And the worst is this. And then add back 1/6. Is that okay? Of course, right? The final answer is going to be 1 minus, right, this whole thing. But I want to leave it to you to write down the number, right? Because we're going to go after the general formula rather than this particular case. Any questions so far? All right. So, like I said, right, the question we're after is this problem, but not 3 men, but n men, right? A generic number. So quiz 7. Repeat the hat problem, but with n men. So now what is so basically right here, I don't write down the final answer because, there's nothing enlightening about that answer. Here we want to write down the final answer for a generic problem. All right. So notice, right, the setup is exactly the same as before. You let EI to be the event that the ith man, right? Ith person gets their right hat. Okay. And we're after, right, the probability of the intersection of all these, which by De Morgan's law is the complement, right, of the union. And now the union will be calculated, right, using the inclusion and exclusion formula. All right. So now let's fill this in. What's P of EI for each I? What's P of EI for each I? So once again, right, from the perspective of any person, they're equally likely, right, to get any of the hat in the pile. So therefore, right, P of EI for each I is 1 over n. Okay. What about EI/EJ? What is it? So here, right, EI/EJ means exactly 2-person, right, getting their right hat. Exactly, right? Sorry. No, right? No. I'm wrong here, right? The I person and the J person getting their right hat, and whatever happens, well, sorry, I'm confused. So you know that the I person and J person getting the right hat, and whatever happens, right, with the rest of the people. So let's write that down, right? So for example, let's say you have 1, 2, 3, 4, etc. to n, right? You know, the first two, let's say, getting the right hat, but the other guys can do whatever they want. So what's the probability of that? The number, right, of possibilities here is, so, right, whatever happens here. So this is all n minus 2 permutations. So basically, right, this is going to be n minus 2 factorial over n factorial. Is that okay? Because basically, right, you fix 2 positions. In this case, right, we say 1 and 2, and then you consider all possibilities in the other positions. So that's n minus 2 factorial over n factorial. Okay. And then this is going to be n minus 3 factorial over n factorial, right? Because you fix 3 positions and then let all the rest commute, so on and so forth, until this is just 1 over n factorial. Any question? Now let's develop this more, right? Well, this obviously is 1. What about this sum? Well, this is 1 over n minus 1 times n times n minus 1, right? But what about this? Here, right, every term is the same value. And how many terms are there? Well, there's exactly n choose 2 terms, right? There. Each of them has value n times n minus 1. And then, of course, you have n choose 3, and then each of them has value. And you know what? Let me just leave the original notation on. Okay, like that. And then of course, right, n choose 2 is what? Well, what's n choose k? Is sorry, somehow my mind is not working. So k factorial, right, times n minus k factorial. Somehow the n choose k notation formula goes blank for me. What is it? So n choose k is it true? N k factorial n minus k factorial over n factorial. Is that correct? Sorry, somehow my mind is not working here with this formula.
It's the other way
Is
around.
it
So
the other way around?
n factorial goes up, and
Okay,
the other
thank
way
you.
goes down.
Yeah, thank you. All right, thank you. So right here it will be n factorial, 2 factorial, n minus 2 factorial, right? Plus n factorial, n minus 3 factorial, 3 factorial, right? So on and so forth. The point is you see that, right? That there's a perfect cancellation here and here, right? Leaving you with what? At each term you have 1 over 2 factorial, 1 over 3 factorial, 1 over n factorial, right? So the final pattern will be 1 minus 1 over 2 factorial plus 1 over 3 factorial, right? And of course you can guess so on and so forth until like that. Okay. Now, is that the final answer? Well, the answer is no, because what we have just computed is the union, right? While what we want is 1 minus that. So the final answer, of course, will be one over 2 factorial minus 1 over 3 factorial, right? So on and so forth. And the good thing is this will switch this, right, to a minus sign. So we get this. So that's our final answer, which is a probability that no man gets the right hat. Okay, any question here? All right, very good. I think we're right on time, so want to stop here. Like I said, I think so homework will be assigned immediately after each lecture, but I'll make the due date I guess the Monday, right? Next Monday, at the end of next Monday. So the homework will be collected once a week, but you don't want to wait, okay, until the weekend to do your homework because it will be piled up really quickly. I just don't want to collect homework every day, whatever. But please try to do your homework as we go along. Okay, so if you have any questions, I'll be happy to answer. If not, I'll see you on Wednesday.
Hello, Professor.
Yeah.
I was wondering, I still don't get why. Yeah. Can we go back to the slides?
Sure. It's showing up, I think. Give it a moment. Okay, yeah. Which one?
Yeah, I still don't get why. How can we calculate this union? Like why it is n minus 2 factorial? Yeah, and minus 3 factorial in this whole.
Oh,
whole
you mean the intersection? You mean from here to there?
Yeah.
Actually, so first of all, it's from here to here, right?
Yeah.
And then, of course, this is just counting up how many terms there are. So which one you have question with from here to here?
Yeah, so
from here to here.
why it is n minus 2 factorial? I don't know where do we get this?
Sure. So it's like this, right? What is this? So basically, it's the calculation of the probability of the ith person and the jth person, right, getting the right hat. So if you list out all positions like this, right, 1 to n, then there are two positions, let's say position 2 and position 4, that you know must be correct. Meaning that you know that 2 must go to 2, 4 must go to 4.
Oh, okay,
Right?
okay, got it. Yeah.
But the rest can be anything. And then, so that's just counting, right? Yeah.
Oh, yeah, okay, thank you.
Sure. All right, we're good. This is you, Rohit. How are things?
Start of class, and I just wanted to ask, what are we submitting for quiz?
You will submit your lecture notes. Like basically, the quizzes are the questions I asked in the lecture. You just submit all those answers to the assignment. Does it make sense?
Yeah, thank you.
Sure.
Have a good day.
You too.